Alright, so for our example of the t-test, we're going to carry on with this example of use of force among male and female police officers. And we're going to say we have one sample that is composed of 33 male officers and a second sample that is 31 female officers. So that's blurry. Right. So we have cameras struggling here. Okay, a little better. All right, so we have these two samples. Our first sample is 33 male officers. Our second sample is 31 female officers. And so our goal here is to use these two samples to try to determine whether among police officers overall there is a difference in use of force by gender or not. And so I'll give you some more characteristics of these samples. Where for sample 1, we can say our N1, or our N for the sample would be 33, so that's 33 male officers. Our mean for the sample, and so for sample 1 here, I'm just putting a little 1 next to each of these, is 6.2 incidents, and we'll say this is use of force incidents in the last month. And our standard deviation for the sample is 1.1 incidents. So here we have a sample. We've taken these 33 officers. We've looked at how many use of force incidents they have over the last month, and this is what we get. Sample 2. N is 31, as we've already established. Our mean for this sample is going to be 5.8. So in our sample of female police officers, we have 5.8 incidents. And our standard deviation is going to be 0.9 incidents. So as always, this is made up data, but this is the number of incidents we have in each sample. The difference, which is going to be an important value for us, in other words, x bar 1 minus x bar 2 is equal to 6.2 minus 5.8, and that comes out to 0.4. So if you think about that difference in mean sampling distribution, we've got our mean of 0, we have a standard error, we don't know what that is yet. We'll say that our difference in sample means, is here at 0.4. So these are all the possible sample means you could get. And so the question we're going to be asking ourselves in this hypothesis test is, if we assume that these two populations have the same mean, and we have a sampling distribution where the overall mean is 0 is the most likely outcome you get when you take two samples from populations that have the same mean. The question here is going to be, is this 0.4, something that's pretty likely, or is it out here, in one of these really unlikely zones? And so these are not written out in t-statistics yet, so these are just the raw scores that I'm writing here. So what we want to know is, is this the situation, or is this the situation? Is our sample mean one of these pretty likely values that you can get, or is it one of these really is our difference in sample means, my goodness, one of these relatively likely values you can get, or is our difference in sample means going to be out here in the tails where it's really unlikely that you'd see a sample mean this big or bigger if we had populations that had the same means? For this hypothesis test, we're going to use an alpha level of 0.05. And again, the alpha level tells you that threshold where you decide something, an outcome in your sample is just too unlikely to have come from the populations described by your null hypothesis. So here we're saying that the difference in sample means that we get in our samples has to be in the 5% of least likely outcomes that you could get if there really is no difference in the population. And I'm just going to write x bar 1 minus x bar 2 here for when I turn this into notes. I feel like this is not as well drawn as it usually is, but hopefully you get the point that we're trying to figure out whether this value of 0.4 is here, close to 0, or out here, because we don't know just by looking at the value. So step 1 is going to be writing hypotheses. And in a two-sample t-test, our hypotheses are generally going to look the same, where your null hypothesis is that the mean for one population minus the mean for another population is equal to 0. So you could also write this as the mean for male officers minus the mean for female officers equals 0. And again, whatever notation you want to use when you do the problem sets is fine with me, as long as you're distinguishing between one population and another population. And your null hypothesis is that the difference is 0. So you could also say here, there is no difference in the mean level of force used by male and female police officers. Our alternative hypothesis is, once you rule out your null hypothesis, what's the alternative? And here, if we can rule out the possibility that they're equal to each other, and so if you subtract them, you get 0, then we're left with the possibility that, if you subtract them, they're not equal to 0, meaning that there's some difference between the population means. Again, you could write this either with 1 and 2 or with M and F to go with the specific problem. Either way is fine. And the key here would be that there is a difference in the mean level of force used by male and female police officers. So again, hypotheses are statements about what might be going on in the population, and we're now going to use our sample data that's written up here to decide whether we have any evidence that tells us that our null hypothesis is not likely to be true, or whether we can't rule it out based on the evidence we have, meaning that it could be true. So step 2 in our hypothesis test is finding a test statistic. And in the example of a two-sample t-test, or in the case of a two-sample t-test, I should say, the test statistic we're going to find is a t-statistic. So just like last week, we found a t-statistic for a single sample mean. Now we're going to be finding a t-statistic for a difference in sample means. And again, that t-statistic is going to tell us how far out our difference in sample means is on this distribution. The equation to find a t-statistic for a difference in sample means looks like this. And it's going to have a similar format to what we've seen before with some slight differences. Where x bar sub 1 is our sample 1 mean, x bar sub 2 is our sample 2 mean, And this big clunky thing down here, S sub x bar 1 minus x bar 2, is the standard error for the sampling distribution. So remember when I introduced this thing, I said it has a mean of 0, but we don't know the standard error of the sampling distribution because it's calculated based on the characteristics of the sample and the variable. Well, that's the standard error that I was referring to. The nice thing for you guys, though, is that calculating the standard error for the difference in means is kind of a pain in the butt. So I don't have you guys do it. There's really no value added, I think, in this class to having you calculate something with a bunch of like square roots and division and just, you know, nobody in the real world would ever do that. And it doesn't really tell you anything intuitively useful either. So instead of doing that, I'm just going to give you this value for any problem like this. But as a reminder, what it refers to is the standard error for your sampling distribution for the difference in means. And it's calculated based on the sample standard deviations and the sample sizes. But again, I'm just going to give it to you. And in this particular question, it happens to be equal to 0.252. So, for those of you trying to follow along with how I got all of these, I'll just say one more time. This is a value I'm going to give to you. It's a pain to calculate. It can be calculated from things that you measure about the sample, including the sample size and the sample standard deviation, but it's annoying to do by hand, so instead I'm just going to give it to you. And it refers to the standard error of our sampling distribution for the difference in means. So once we have that, the rest of this is pretty easy. So this looks similar to other equations to find test statistics that we've seen before. So our z-score, our t-statistic for the one sample t-test. And all we really need to do now is plug things in, because we have all these values. So we know that our first sample mean is 6.2. Our second sample mean is 5.8. And so sample 1 mean is just the mean for male police officers, so they had 6.2 use of force incidents. And then sample 2 is the mean for female police officers who had 5.8 use of force incidents. We'll plug these in, so to get our t-statistic, we're going to have 6.2 minus 5.8. And you should notice that's just the difference also that we calculated before. So we had 6.2 minus 5.8 is 0.04. So it's the difference that goes on top. And then our standard error for the sampling distribution, which will be given. And if you do this, you get 0.4 on the top, which is that difference that we already saw, divided by 0.252. And that comes out to 1.59. So t equals 1.59, and this is our test statistic. Alright, so now we're really back in pretty familiar waters as well. So we had our sampling distribution for the difference in sample means. That had a standard error of 0.252 and a mean of 0. We know that our sample difference, is at 0.4, And we're not really sure exactly how far this is going to be, you know, whether it's going to be in the tail or here, so I'm just kind of drawing it in a spot. Once we find a test statistic, we are standardizing everything, just like when you find a z-score or find a t-statistic elsewhere. So now, instead of having this distribution where we're counting in use of force incidence, we're changing everything to t-statistics. So it's like going from feet to inches, as we've done many, many times now, where we go from the units that we're measuring things in our sample to some standardized distribution. And our t-statistic that we calculated is 1.59. So we've got our standardized distribution. It's all in t-statistics now. And we're going to try to figure out, again, whether this sample we have, which we can describe on this standardized distribution like this, is one of these really unlikely differences in sample means that we could get, or whether it's one that would be pretty likely if there was truly no difference between the two groups in the population. So as always, the nice thing about working with the t-distribution or the normal distribution once it's standardized is that the standardized distribution is the same every time, and the area under the curve for different t-statistics is known. So with that in mind, we are going to now go to our next step, which is deciding whether to reject the null hypothesis. So I'm just going to draw this out again. Just like last week, once you have your t-distribution and your t-statistics, where we're at 1.59 here, everything is standardized. And so you can find a p-value the same way that we did last week. Where again, the p-value refers to the probability of getting a sample value as extreme or more extreme than the one you got. That's for one of these two-tailed tests where we're interested in a difference that could go in either direction. So we didn't say that sample 1 is going to be bigger, we didn't say that sample 2 is going to be bigger, we just said that they're going to be different. So because of that, we're going to allow samples that are have a bigger sample 1, and that would be on this side, and we're going to have samples that have a bigger sample 2, that would be on this side, both be able to count as evidence against our null hypothesis. If we didn't, we'd only be looking at one side of the graph. So the p-value for a two-tailed test like this, where we're willing to consider samples that are extreme in either direction, so either big or small, we look at the area under the curve that's past our test statistic on the side that our test statistic is actually on, and we also look at the area under the curve that's past our test statistic on the side that it's not on. Because that's going to give us the probability of getting a difference in sample means as extreme or more extreme than the one we got. So our shaded area is our p-value. That's the probability of getting a sample statistic as extreme or more extreme than the one we got. Where our sample statistic here is t, and our t is based on the difference in the means that we saw. So as it turns out, when t is equal to 1.159 and we have the sample sizes that we do, so we're taking into account, our uncertainty and all that. P comes out to 0.1178. All right, so we're almost there, but we're not quite done yet. And if you remember from last week, we use our p-value to tell us whether our sample falls in that really unlikely zone or not. With an alpha level of 0.05, we're only looking at the 5% of least likely samples statistics. As evidence that our population doesn't look like what we're saying in the null hypothesis. So if our sample falls, in the 5% of least likely values, we would reject the null hypothesis. In this case, though, our p-value of 0.1178 tells us that our sample values here actually fall in the 11.78% of least likely sample values. Because how we interpret this p-value is that sorry, I'll finish that sentence after I write this. So how we interpret our p-value is that if the null hypothesis were true, so if the difference in the populations is really 0, there's an 11.78% chance that we would see a sample statistic as extreme or more extreme than the one we got, if that null hypothesis were true. So if there was no difference, we would see a difference in sample means like the one we got, or bigger than the one we got, 11.78% of the time. So it's in that 11.78% of least likely possible sample means. This means that our difference in sample means here doesn't fall into our threshold where we reject the null hypothesis. So we're saying it's still pretty likely that we would have gotten this difference that we actually got of 0.4, if there was really no difference in the population. So it just so happens that in our two samples, our male officers were using more force than our female officers, but the difference isn't big enough to give us evidence that there's a difference between these two groups in the population. All right, so I'm also going to just write some of this out. So we'd interpret our p-value as saying that if male and female officers use the same amount of force in the population, we would see a difference in sample means as large or larger than 0.4, that's the one we got, about 11.78% of the time. Because our p-value is larger than our alpha level, we fail to reject the null hypothesis. So our p-value is larger than our alpha level, which tells us that our sample difference here is something that's pretty likely you'd get if there was no difference between the population means at all. So we fail to reject the null hypothesis because our p-value tells us that that's where our sample falls in this distribution. And it's not in that 5% of least likely possible sample means. All right, and then you're done. So you would take this test and conclude that based on the available evidence, there's no reason to believe that there's a difference in the amount of force used by male police officers and female police officers. And that's it. As a reminder, you would never say that you accept the alternative hypothesis, even if you fail to reject the null hypothesis. The idea is that we have failed to come up with any evidence that would tell us that this true population difference of 0 is not the case, but we don't actually have any evidence in favor of anything else specific. So we have just failed to disprove something. All right, so as promised here, I'm also going to just go through a quicker example of the two-mean hypothesis test. If you're already feeling totally comfortable with this, you can skip back to the video. If not, tag along. And so I'm going to go through the example that just has less of the drawing and explaining and so on, and just more of the specific steps. All right, so we're going to say that in this example, we want to know whether the criminal defendants are sentenced differently by two different judges. We've got Judge 1 and Judge 2. And we're interested in whether they're giving out different sentences or the same sentences. And we're going to look at the many, many, many defendants they've sentenced. So for Judge 1, we have 150 defendants. For Judge 2, we're going to have 120 defendants. And for Judge 1, we had a sample mean of 10.3 years. So in your imagination, you can kind of fill out what crimes we're looking at or whatever. I'm just going to focus on the numbers here. So in our sample standard deviation is 4.1 years for Judge 1. For Judge 2, we have a sample mean of 6.5 years. And we have a sample standard deviation of 3.8 years. So here we're going to be comparing sentences given out by these two judges, with the idea being that these are samples of sentences that sort of represent the broader population of each judge's sentence. So of every sentence that Judge 1 has given or could give, this is 150 of those possible sentences. Of every sentence that Judge 2 has given or could give, this is a sample of those. So the idea is that we're looking at these samples of sentences given out by these two judges to kind of get at their sort of underlying or overarching punitiveness towards offenders. We're going to stick with our alpha level of 0.05 as the standard one. And so our final thing here in just looking at the samples is to come up with the difference. Since the two-sample t-test is all about that difference in sample means. So here we're just taking our x bar 1, subtracting x bar 2, and that comes out to 3.8 years. So the difference in sample means is 3.8 years. And the question we're going to answer with the hypothesis test is this difference of 3.8 years large enough to give us evidence that Judge 1 and Judge 2 assign different sentences to defendants? So step 1, we're going to write out our hypotheses. And so our null hypothesis is that the judges give the same sentences, and our samples that we chose here just happen to have picked a bunch of people that got higher sentences from Judge 1 and just happen to have picked a bunch of sentences that got, a bunch of defendants who got lower sentences from Judge 2. So our null hypothesis is that in the population, in the population of sentences given out by Judge 1, And the population of sentences given out by Judge 2, there's no difference. And I will just make a quick note here, too. You can note that I'm sort of talking about population in a different way. So just as a reminder, population doesn't have to refer to people. It can really be any set of things that you're interested in. So here we're interested in just the total set of sentences, that Judge 1 could give out to people, or that Judge 2 could give out to people. Alright, so our hypotheses are the same as they're going to be every time for this test, which is that the population mean for one population minus the population mean for the other population is equal to 0. We're saying that if you look at all the sentences that Judge 1 has given out or could give out, and all the sentences that Judge 2 has given out or could give out, if you took the mean of all those sentences for each one, subtracted them, you get 0. In other words, there's no difference. Our alternative hypothesis is the opposite of that, so we're going to say that if you did all that and subtracted them, you'd get something other than 0. So there is some difference. Between how these judges assign their sentences. Step 2 then is to find a test statistic. In our 2-sample t-test, the test statistic that we look for is t. In future weeks, we'll meet some other test statistics, but this one's t. We're going to use the equation that we saw in the last example, where we're subtracting our first sample mean and our second sample mean, and dividing by the standard error for our sampling distribution for the difference in means. And here we're going to assume that that standard error is equal to .486. So this value again is something that is calculated from characteristics of the sample, specifically your sample standard deviations and your sample sizes, but because it's annoying to calculate by hand, I'm just doing it for you and giving you the value. So I'd rather you just focus on, the things that are sort of consistent across the hypothesis tests and, what they actually mean than get bogged down on it. Alright, so we have our values here now to plug into our test statistic equation, where to find t, we're going to take our first sample mean, which is 10.3, our second sample mean, which is 6.5, and we're going to divide by our standard error for the sampling distribution, which is 0.486. If you do this, the whole numerator of the equation, so the top half of the equation, is equal to the difference that you already calculated. So it's 3.8, and then we're dividing that by 0.486. This comes out to 7.819. So this means that on our standard t distribution, where we're counting in t statistics, our sample difference is somewhere out here at 7.819. And the longer you do this, the more you start to be able to just kind of eyeball what's going to be reject and what's going to be a not reject. You can try to take a guess if you'd like right now, but for now we're going to keep going through. Alright, so with step 3, you then decide whether to reject the null hypothesis. Again, so our question that we're going to be answering in step 3 here is whether this difference in sample means that we found is in that 5%, because we're working with an alpha level of 0.5, that 5% of least likely differences that you'd get if the null hypothesis were true and the judges were giving out the same sentences on average. As it turns out, for t equals 7.819, the p-value is really, really, really small. It's less than 0.0001. This means that in our distribution, the chances of getting a value that is greater than 7.819 or less than negative 0.7819 are really, really, really small. And in fact, there is less than a 0.1% chance that you would get a sample value that extreme. So our p-value here, which is even less than 0.0001, it's so small that the computer doesn't bother to spit out what it is. It's definitely less than our alpha level of 0.05. So we easily reject the null hypothesis. And we say that the sample difference that we got is in this, least likely 5% of cases, what we're considering evidence, and so we're going to consider it to be evidence that the true population mean is not equal to 0. When you reject the null hypothesis, you can say that the difference you found is statistically significant, so that's what we would call that here. And that's it, that's your hypothesis test. So by going through, we have established that this is what our situation is. Our sample difference that we found, so this difference of 3.8 years between Judge 1 and Judge 2, is way too big to have reasonably come from a population where these two judges are actually sentencing people the same on average. And so we have evidence that, Judge 1 is giving out more punitive sentences than Judge 2 on average. The last order of business for today, and what I'm going to go back into the PowerPoint for, is to now talk about how to do a t-test using a statistical program. And just as a heads up, this is going to be on the problem set, but more importantly, the reason that I'm showing you this now is that output like this, and like we'll see in the next couple of lectures, will be used in that applied data analysis project that's on the syllabus and that I mentioned would be coming up towards the end of the semester. So I'm not going to tell you what it is yet, but that's a reason to pay attention to what I'm about to do now. And before I do that, just as a reminder, it sounds very intense because it's called an applied data analysis project, but it's going to be, I think, around the same level of time and difficulty as a problem set, just in a different format. Alright, so back to that PowerPoint.